Alright, so this is section 9.1, the very first section in this course. It talks about limits. So here's an example of a problem where you've got a function that is a rational, it's called a rational function because it's a fraction of polynomials. And you can factor the top and the bottom and cancel and simplify it. Now if you take the limit, and we're going to be taking the limit as we approach negative 2 here. So if you approach negative 2 from the left and you get closer and closer and closer to negative 2, what happens to the y values, or f of x? Well, it gets closer and closer to negative 5. And the same thing with negative 2 from the right, negative 1.9, 1.99, and 1.999. You get closer and closer and closer to negative 5. So the idea here is that if you're taking a limit, what value is it approaching as you approach a certain value, in this case negative 2, what is the y value approaching? If it approaches some finite number, some real number, then you can say the limit exists. Well, if you graph this thing, you can see it's a graph of y equals x minus 3, but it has a hole in it at negative 2 because the original function is not defined at negative 2. So it actually has a hole there. Now if you approach it from the left or from the right, you approach a y value of negative 5, and that agrees with what we saw in the table. And so here's how you would evaluate it using algebra. You'd take the function and you'd factor it, cancel, and when you simplify it as much as you can, see if you can plug in the number you're approaching into the polynomial, and if you can, without dividing by 0, and you happen to get a finite number, then you can say the limit does exist. Alright, these are 3 examples of limits that exist. Alright, so we're approaching the y value, or x value of 2, so you come at this from the left and from the right, and you can see it approaches the y value of 3. And so the limit as x approaches 2 equals the y value of 3. Now, in this case, f of 2 also equals 3. Now this one, if you approach x equals 2 from the left and from the right, you're approaching a y value of negative 1. Okay, so the limit equals the y coordinate of negative 1. But notice, if you plug in 2 into the function, you don't get an answer because it's undefined. There's a hole there at 2. Then the third possibility is if you're approaching x equals 2 from the left and from the right, you're approaching a y value of 1. But at 2, you get a y value of 4. And so the limit equals 1, and at the point itself equals a totally different number. So this is the basic idea of a limit. A limit says, a good way to describe a limit is talking about 2 men that meet for breakfast every morning at a diner. Okay, let's say the diner's right here at this point. So the one guy is approaching the diner from this direction, another guy is approaching the diner from the other direction, and they meet every day at this one diner. So they approach from the left, they approach from the right, and they meet at the same point, so the limit exists. Now let's say they come to meet at this diner, and the diner is supposed to be right here, but when they approach the diner from either side, they find that there's a big hole in the ground. The diner is gone. Well, that means that doesn't matter whether the diner is there or not, because they both approach the same y value, in this case negative 1, and the limit does exist. So we don't care what's happening at that point. We only care what's happening as we approach that point. And then what about here? Let's say they're approaching the diner and there's a big hole in the ground, or the diner's missing and they found out that somebody has moved the diner to a totally different address. They picked up the entire building and moved it somewhere else. This limit also exists because we don't care what happens at that point, in this case x equals 2. We only care about what's happening as you approach from the left and the right, and that they approach a finite number and that they agree with that. Both sides approach the same number. Now when we talk about limits, we're going to be talking about one-sided limits. With this little plus here, that means you're approaching some constant number, c, from the right. And for us, from the right, for 2 would be 2.1, 2.01, and a limit from the left with this little negative sign there, that means you're approaching it from the left. So 1.9, 1.99, 1.999, that sort of thing. All right. So when one or both one-sided limits fail to exist, then the limit does not exist. When the one-sided limits differ, then the limit does not exist. All right. In other words, for a limit to exist, you have to find the limit from the left and the limit from the right, and they will equal some number, in this case L and M, and they have to equal the same number. And in that case, then you can say that limit does exist. All right, so here's 3 examples of limits that do not exist. So this first one, if you're using this function and you're approaching from the right and approaching from the left, approaching from the left you go off to positive infinity, approaching from the right you go off to positive infinity. Those are not finite numbers, so you say these left-handed and right-handed limits do not exist, and the function, the limit does not exist since the function does not approach a finite number. Now here, if you approach from the left, you get minus infinity. Here you get positive infinity. Both are not finite numbers, so you can say the limit does not exist. All right, and then this one, this is a piecewise function. If you approach from the left, you get a finite number of 0. If you approach from the right, you get a finite number of 3. And the left and right-handed limits do exist. They do equal a finite number, but because they don't agree with the same number, then the limit itself at 2 does not exist. So, a limit. What is a limit? A limit, as x approaches some constant for some function, equals some number L, only if 2 conditions are satisfied. Number 1, the limit L is a finite number. It can't go off to infinity or minus infinity. And the second part is the limit as x approaches that number from the left equals the limit as x approaches that number from the right, and they're equal to each other. Now this is the other idea I was talking about the diner. The limit itself and f of c at that point are independent. When the limit does exist, we can have for the function at that point, it can equal the same number as the limit, or it can be completely undefined at that point, or it can be defined but a different value from that limit. And that's what we saw in the earlier earlier question. So what are some of the different limits, properties of limits we can say? So let's say k is some constant, and the limit for some function f equals some finite number L, and the limit of g equals a finite number m. All right, so then we can say the limit as x approaches some constant of just a number equals that number. So think about this. This is just a graph of a constant like y equals 5. Okay, if you've got y equals 5, it's a horizontal line. And it doesn't matter where your c is. Let's say your c is right here. If you approach from the left and from the right, you're always going to be approaching the y coordinate of 5. So that's why it equals k. K equals k, or 5 equals 5. Now the limit as x approaches c of x equals c, well that's just a graph of y equals x. See, 45-degree angle there goes through the origin. So if you're looking at the value 3, then the y-coordinate is also going to be 3. If you're looking at the value of minus 4, the y-coordinate is also going to be minus 4. So if you approach 5, plugging 5 into the function, you get 5 for the limit. And so the limit of x equals just c, whatever your number c is that you're approaching. Now the limit of one function plus or minus another function is just the addition of each separate limit itself. So you can take the limit of f and the limit of g separately and then just add those answers together. Same thing with multiplication. If you got the limit of 2 functions that are multiplied, take the limit of f, take the limit of g, and whatever answer you get, you just multiply them. Same thing with the limit of a rational function. The limit of the top and the limit of the bottom, whatever they are, that's your answer for the limit of that fraction, assuming the denominator is not 0. And then the limit of the nth root of a function is just the nth root of the limit of the function. And we know the limit of f is just L, so it's the nth root of L. Polynomial functions, you'll find that polynomial functions, the limits behave very nicely. So if you find the limit of a polynomial, you just plug in c into that function. Direct substitution. Same thing for a rational function. If you got a rational function equals the limit of two functions, it's just f of c over g of c, assuming g of c does not equal 0. So what about example 3 here? They're taking the limit as x approaches -1 right here of this function. This is the graph of it. So if you look at this, coming at it from the left and coming at it from the right, you're approaching a y value of +1. But also, remember I said since this is a polynomial, you can just plug in that number into the function itself. And when you plug -1 into this function, you get -1 cubed minus 2 times -1, simplifies down to 1. And then same thing for a rational function like this. If you're looking at x equals 4 right here, approaching from the left and approaching from the right, it equals a y-coordinate of 0. Well, it also will equal g of 4. You just plug a 4 into here and you get 16 minus 16 over 4 minus 2, which is, what, 0 over 2, or 0. You always have to make sure you're not dividing by 0. Now with that last type of limit, where you've got something over something else, a fraction of polynomials called a rational function, there's two possibilities, two possible cases. First, if the limit of the top is 0 and the limit of the bottom is 0, is type 1. And if the limit of the top is not 0 and the limit of the bottom is 0. These are two specific cases where you can't use direct substitution because you're dividing by 0. So, if you've got the top is 0 and the bottom is 0, that's called the indeterminate form 0 over 0. So we can factor it like we did earlier, reduce the fraction, and then find the limit of the expression if it exists, and we did that earlier. The second one is where the top is not 0 and the bottom is 0. And so now you've got a problem because your denominator is going to get infinitely small and the numerator is some finite number, and so what happens is this thing explodes to positive or negative infinity, unbounded, and you end up not having a limit, but you also end up having a vertical asymptote at that number, whatever number you're approaching. So here's an example of 0 over 0 type 1, where the top is 0, the bottom is 0. And like I said, you can factor it, cancel, simplify, and then you can do direct substitution at this point because you're no longer dividing by 0. And this one again, you can factor the top and the bottom, and it simplifies down to here, and now you can do direct substitution and you get a very specific answer. And notice with each one of these you can look at what you're approaching at 2, and coming at it from the left and right does equal 4. And here you're approaching 1, coming at it from the left and the right does equal -1/2. The second type of indeterminate form is some constant over 0. So let's look at this one. This one's trickier because we can't do algebra because, well, we could if the top factored, but it doesn't. It doesn't reduce like we would want it to. So let's look at it using a table. If you approach 1 from the left and 1 from the right, look here, this goes to -infinity and this one goes to positive infinity. And that agrees with this right here. It's going out to -infinity forever and up to positive infinity forever. And thus the limit does not exist since the left-handed and right-handed limits do not exist and they do not approach a finite number. Also note x equals 1 is a vertical asymptote. So example 6 talks about removing pollution from the emissions of a smokestack. So if you look at this problem, if you approach 100, as in 100%, you're going to be dividing by 0 because P is the percentage of the particulates you want to remove from the smokestack. So if you only remove 10% of the pollutants, it only costs you $811. 50%, it costs you 7,000 something. 90%, it costs you 65,000. 99, now you're up to 750,000. And then 99.999, you're talking about $750 million. And then if you want to remove 100% of the pollutants, it's undefined. So what happens as we remove more and more pollutants, as x goes to 100, your function goes off to infinity. In other words, the costs become astronomical. So as we remove as much of the pollutants as possible, the costs increase without bound. Now what about a piecewise function? Well, a piecewise function, if you look at it, they're asking you to analyze this thing, the limit as you approach 1. So if you look at the limit here from the left, you see it approaches 2. From the right, it approaches 3. So this limit is not going to exist. But let's look at it in other ways. Let's look at it from a table. As we approach 1 from the left, we approach 2. And that agrees with what we saw down here, that we approach 2. If we do algebra, we see that we can plug in 1 into the polynomial and we get 2. Now what about from the right? We would expect to get 3. And what happens here is the y-coordinate approaches 3. Then if you take the function and plug in 1 into the polynomial, you get 3. Now notice if you come at it from the left, you have to use values that are less than or equal to 1, so you're going to use x squared plus 1. If you come at it from the right, you're using x plus 2. So with the piecewise function, you have to be careful which part of the piecewise function you're going to plug into your limit. So basically the limit does not exist since the one-sided limits do not agree. And looking at the graph, we can see that the limit does not exist. Example 8, they ask us to look at two different limits, and they want us to do it graphically, numerically, and algebraically. So the first one is this guy right here. The limit as x approaches 5 of this polynomial fraction. So if you graph this, you can see from the left and the right you're going to be approaching 3, y value of 3. If you look at it on a table, you can see that as you approach 5, in either case you approach a y value of 3. And then if you do the algebra and factor and reduce and then finally plug in 5 in for x, you get an answer of 3. And so all three of these are giving you the same answer, algebraically, graphically, and numerically. B is looking at this one. Okay, this one you're dividing by 0, so you got trouble there. Well, if you look at this one at -1, it's undefined. It doesn't have any value at -1 because there's a vertical asymptote at x equals -1. So we can say the limit does not exist since it doesn't approach a finite number. If we approach -1 from the left or from the right, we approach positive infinity or minus infinity, and thus it does not exist. And for the same reason, we can say this limit does not exist because we're dividing by 0. Alright, so now when you look at problems in each section, I will be doing very specific problems out of each section's homework. And the problems that I choose are very specific to your WebAssign homework. And this is the way you should do it. You should get two different devices, log on to one device, and watch this YouTube video. Obviously, you're already doing that. And then with the second device, log on to your WebAssign homework assignment for 9.1 in this case. Okay, and so watch how I do this first problem. And once I'm done explaining how to do this first problem, hit pause on the video. And then turn to your other device and answer the first question on your WebAssign homework assignment. Once you're done with that first question, turn back to the video and hit play and watch how I answer the next question. Then hit pause and then do question number 2 on your WebAssign. And then hit play over here, watch how I do question 3, hit pause, turn to your computer and answer question 3. And this way you can work your way right through your entire assignment by seeing an example of how you want to answer your question on the computer homework. Alright, so this one says in problems 1 through 6 a graph is given and a c value is given. Use the graph to find the following if they exist. Find the limit as x approaches that number c, and ask what's happening at f of c. Alright, so this one is c equals 4. So here's 4, and you can see from the left and the right you're approaching negative 8. And f of 4 does equal negative 8. Okay, number 4, c equals 20, so you're approaching 20 from the left and the right, and you're going to get a y value of 10. But notice f of 20 has a hollow circle there, so it does not exist. Number 5, you're approaching minus 2 from the left and the right. You would approach a y value of 0. Okay, so the limit equals 0. And notice f of negative 2 equals positive 2, not 0. And number 6, negative 8, you're approaching negative 8 from the left and the right. You approach a y coordinate of 0. And at negative 8, you approach a y value of negative 6. Alright, so the same idea. Well, this one is asking you to do 4 different things. Find the limit from the left, limit from the right, and the limit itself, and then f of c. So the limit of minus 10 from the left means you're coming at it this way, and you go off to infinity. Limit from the right with this little plus sign means you're coming at it from the right, and it goes up to infinity. And since those two are not equaling a finite number, you can say the limit at minus 10 does not exist. This is the left-handed limit, right-handed limit, and the limit itself at that point. And then f of minus 10 is undefined because it does not exist. Okay, number 10, from the left you get 3, and from the right you get minus 6, and at the point you get minus 6. Notice since the left and the right are different values, the limit itself does not exist, but the f of that number does equal a specific number of minus 6. Alright, so now they want us to analyze polynomials and rational functions here. So remember, you can just plug in the value directly. So you take the polynomial and you plug in minus 35 in for x and simplify it. You plug in minus 1 into the polynomial, simplify it, and you get your answer. Same thing with rational functions. You only have to worry about if you're dividing by 0. So just plug it in and hope you don't get division by 0. When you simplify it, you don't, so that's your answer. And then here, if you can factor it, do so and simplify. And then you can plug in the minus 4 into the function and you get your answer there. Same idea here. You simplify and you get down to here. Now you can do what's called direct substitution. Plug in 7 in for x and simplify it and you get your answer. Same thing here. We're factoring, simplifying, and now we can do direct substitution. We're no longer dividing by 0 and we get an answer. On this one we factor, cancel, and we can do direct substitution, and we're not dividing by 0, we're dividing into 0, which will give you 0. That's the legitimate answer. Now this one asks you to analyze this thing where x equals 3, which is the interesting point of this piecewise function. So coming at 3 from the left, you're going to use x less than 3, so you got to use 10 minus 2x, and we analyze it. Then coming at 3 from the right, we use the second line, x squared minus x, and we plug in 3 into that and we simplify it. Since they do not agree, we say the limit does not exist. Now with this one we're looking at minus 1, so minus 1 from the left, this is x squared plus 4. It's kind of hard to read. X squared plus 4 over x. If you're looking at minus 1 from the left, you're using the top function, and you do direct substitution, you get an answer. If we come at it from the right, we're using the bottom one, and we do direct substitution and we get the same answer. So we can say the limit exists because these left and right-handed limits are finite answers and they are the same answer. Okay, number 44. They ask us to analyze this picture for x equals 5, so you're thinking about minus infinity and positive infinity. So the limit is not going to exist. We can just see the graph and see that, but if we look at it using the table, we can see that this goes off to minus infinity and this goes off to positive infinity. So we can say the limit from the left goes to minus infinity, the limit from the right goes to positive infinity, so the limit does not exist. Using algebra, we can factor the top and bottom and cancel, but notice we still have problems with division by 0 here. If you plug 5 into this, you don't get an answer, you're dividing by 0. So you have to say the limit does not exist. But this answer using algebra is the same answer we get using the table, which is the same answer we get using the graph. Alright, 53, they ask us, they say if the limit of f plus g equals 5 and the limit of g equals 11, find the limit of f. Well, the limit of f plus g equals the limit of f plus the limit of g, but we know the limit of g is 11. And we know the limit of f plus g is 5, so if the limit of f plus 11 equals 5, you can subtract 11 and you get the limit of f is minus 6. So now we know the limit of f is minus 6, the limit of g is 11. So the limit of f squared minus g squared is just the limit of f quantity squared minus the limit of g quantity squared, which is negative 6 squared minus 11 squared, which gives you minus 85. And then the limit of this is just 3 times the limit of g over the limit of f minus the limit of g. And g is 11 and f is minus 6. Simplifying it, you get your answer there. This one is asking you to take the limit as x approaches 100. And this is a polynomial, so you can do direct substitution and you get a very specific answer. And this one says they're talking about the monthly sales for a new person depending on the number of hours of training. And so they're asking you to find the limit as x approaches 4 from the right, and then the limit of 10. So the limit of 4 from the right is greater than 4, but you're getting infinitely closer to 4, and you look like you're approaching 13.25. Okay, if you look at this, 4 from the left, it does seem to be approaching negative 13.25. Okay, and then B, when you take the limit, if you take this guy from the left and from the right, you can see that you're getting infinitely closer to 13.4 either way. I didn't have to use a table. I could have just done direct substitution with 10. I could have done the limit as x approaches 10 of 9 over x plus 10 plus x over 4. And since that is a series of either polynomials or rational functions, I can do direct substitution. Get 9 over 10 plus 10 plus 10 over 4. Okay, and that's 0.9 plus 10 plus 2.5, which will give you 13.4. So I didn't have to look at it from the left and right. I didn't have to do this whole table thing. I could have just done direct substitution because this is a rational function, this is a rational function, and 10, believe it or not, is a polynomial. It's a boring polynomial, but it is a polynomial. So you can do direct substitution as long as you're not dividing by 0.